Um, and it's my pleasure to welcome you to the next lecture on data warehousing and data mining techniques. And last week we were talking about the basics of data mining. So what is a data mining? What are the typical applications of data mining? What are the life cycle elements of the data mining? And then how is the data warehouse built actually? Today, we want to go into more architecture, into more data modeling, and see how is this different and how does this change from the typical relational database view. So we will talk about different architectures. We will look at the architectures in practice and see how they are actually done. And we will talk about storage and modeling of the underlying data and how this is done. So these are the basic topics for today. Let's start with the basic architecture. If you look at the full architecture, you basically have five different areas that you have to address. One is the data sources. This is the operational data systems, right? Usually OLTP databases that are in current use by the customers, by the human resources management, by enterprise resource planning systems, or whatever. From these, you extract the data into what we call the staging area. So we had a short glimpse of the ETL process last time. And the idea is that the staging areas is where you prepare the data. This is not done on the base systems because it would stress load on the base systems. You don't want load for the data warehouse, for the analytical queries running on the base system, right? I mean, there was the Walmart example where the cash registers were frozen for 10 minutes or something because there was a big analytical query running at the time, right? This is not what you would want. So this is the staging area. In the staging area, you can manipulate the data, you can transform it, you can work with it, and then you get into the actual warehouse. And in the warehouse, you have basically three kinds of data. You have the base data, you have the raw data that is there. But to speed up your access to the data and to speed up analytical queries, you need pre-aggregations. So you need a couple of aggregations that are pre-computed and ready to use, right? This is often called summary data. And then you need to know how this data is kind of built. What does it mean? Where does it come from, right? This is called metadata. So metadata is descriptive data about the data that is in your data warehouse, right? These are the three kinds of data that you have. Then you have the data marts. Data marts are special views on the data warehouse with respect to a certain topic or with respect to a certain point of view. Whereas in the warehouse, you've got all the data of the whole company. In the data mart, you get specialized sections of it. So for example, human resources needs a different selection from the data than marketing does, right? One needs customer data, the other needs employee data, right? They are both here. But they are here among a huge amount of other data. So getting them into the specialized data marts is a very good idea. And then you need the application interfaces, the users, where you do reporting, where you do analysis, where you do all the interesting stuff, right? And you need to support that with different systems. So this is kind of the full data warehouse view. So let's start. First are the operational data sources, right? And these are the databases that serve the daily operations of your company. So this is where every sale in a Walmart is stored. This is where every bank account is managed in a banking system, for example. This is where the customer management of insurance companies is done, right? So this is where the actual work happens. And this is very classical relational database technology. So OLTP databases, the online transaction processing databases, are very relational in what they do, right? and it might kind of make you wonder. But this technology has been around since the 70s. End of the 70s, the first relational databases were actually incarnated. Oracle was among the first. And they're still here. So after 30 years of databases, of database development, we're still in the relational system because it works, right? It works very well. It reflects very well what you are doing on this operational stage, right? And the queries, you can of course also put queries in these productive systems. But they're usually small queries. They're simple queries. They're queries like, okay, how many of this thing we still have in stock, right? Or is this customer a regular customer or is it a new customer, right? So very simple, very easy query, easy to run, quick to run, and not long-running transactions, right? Not something with several joins and complex queries, but rather simple lookups. And then, of course, you have a lot of inserts, you have a lot of updates, you have a lot of deletes, because something is taken out of the stock and sold, right? So it has to be inserted into the sales register, it has to be taken, deleted from the stock register. You might update prices because you have a promotion on toothpaste or whatever, right? And then you do a 10% discount, or you have frequent buyers or something like that, and they get 5% discount or something like that, right? So this kind of updates that you do, deletes, insert, and this is what happens in relational databases quite a lot. The staging areas has a separate copy of the new data. So we were talking the last time about the initial extraction, where you, for the first time, crawl or the system decide what you want to have. And then you have the maintenance process. So you need to maintain the data warehouse in a stable condition, right? It has to have maybe not the newest data, but recent data. It may not be on like daily basis that all the data is in there, but on a weekly basis or at least on a monthly basis, it should not get too stale, right? So you decide when you want to extract and when you want to insert new data into the data warehouse. And to work with these data, you will see in a minute that the requirements for building the actual warehouse are different than we had in the operational stores. So things can be in different formats, right? Data formats, for example. The same information stored in different systems can be extracted in different types or different data formats, and then has to be adapted before being loaded into the data warehouse, right? This is what you do in the staging area. Same goes with the integration. You might get the same information or kind of very similar information from different sources. So every store has a certain database, a local database that records its sales, right? And then you have to collect this data and kind of present it in an integrated way. Same goes for the cleaning. You can't just take what you get from the extractors from the systems, but you have to look at it closely. You have to find out whether there's something in there that looks fishy, right? So customer information that just can't be wrong because somebody says he lives in Greenland or somewhere else, right? And you go, look, this cannot be true. And the reason why you call about data cleaning so much as opposed to the operational systems is that in the first place it hurts your analysis. So the more incorrect data you have, the worse your analysis, and thus your predictions based on this analysis will be. But on the other hand, we said that we hardly ever delete something from the data warehouse. So if if you insert incorrect data into the data warehouse, right, it will be with you forever. It will stick in your data warehouse, and for the next 10, 20 years, you will have these data sets around. And this is rather care for them, right? one very important thing in the staging area is some wisdom, some chef's wisdom, right? And the chef's wisdom is that in a restaurant, the customers, or the guests, should never visit the kitchen, right? Because they're just getting in the way. You know, they're just not welcome in the kitchen, because they're kind of touching things and making a big mess. You know, and you have to go around them all the time. It just doesn't work. And this is the same for the staging area. If you are responsible for building up the data warehouse, right? Keep everybody out of the staging area. Even if they say, no, I need the newest data and I don't care how clean it is or is it already ready, you know, I just want to make a couple of analysis on it to see the newest trends or something like that. Just say no. You know, nobody touches that data. Because even if they say they just read and they just, you know, they will kind of hurt the process of your cleaning. They will hurt the process of what you did and so on. So only really data warehousing professional should be able to enter the staging area and perform changes on data in the staging area. Definitely not analysts and not even the guys from the operational stores, right? Because it's just not their business. So this is one important thing that we can learn from restaurants, which is good. Okay. Then we got the central part, the data warehouse, right? And the data warehouse stores the cleaned raw data. So everything that we prepared in the staging area is transported, is loaded into the data warehouse. But then it needs some more to do these analytics, right? It needs derived, and that means aggregated data, right? And these aggregates are kind of very interesting to make queries short running. As you will easily see, they introduce redundancy, right? So if I know every sale, I also know the sales per region, right? Or the sale per quarter or something like that. I can just perform a query that actually does that, right? Group by region, as easy as that. However, every group by, every join, every aggregation costs a lot of time. This is perfectly okay if you have gigabytes. This might become a problem if you have petabytes, right? So optimization of queries and pre-aggregation is very important for the performance of your data warehouse, right? So whenever you can, avoid computing aggregates at query time. On the other hand, you have this typical trade-off, right? The more aggregates you pre-compute, the slower the loading process will be, because loading involves indexing, access paths, aggregate computation, right? And storage of all that. So you have a lot of storage space that you need to store all these aggregates. You have a lot of time that is consumed in the loading phase, and it really depends on your data warehouse and on the use of the data warehouse. What is often queried, you know, like what type of query comes often? Do the people really query very often by region? Do they want to know the countries, or do they rather go, okay, everything in Europe or everything in North America or something like that, right? If you see trends in the queries, you can decide which aggregates you need and which aggregates it is worth keeping up. It's kind of the same with indexes. An index is always a nice thing to have, right? And since data warehouses are usually prepared for reading, it's a very good idea to put in as many indexes as you can, right? You don't write, you don't update, you don't have index maintenance costs. You just maintain the indexes while loading, right? And in the end, it speeds up your access, your reading access, that is. So keeping up a lot of indexes is a good thing. On the other hand, indexes need space, right? And especially if you try to put the indexes in main memory, which is rather usual, to make efficient use of them, then your space is usually limited, right? So you have to decide which ones to create, which ones do you want to load. Yes?
Is the aggregation triggered by some defined rules, or is it manually done by the professional data warehouse professionals?
No. Of course, you create rules and you decide for what should be materialized, right? And whatever is materialized is then automatically generated during the loading process, materialized in the data warehouse, and that's it. Like an index, right? You decide which columns to index in a normal database, and then every time something is inserted, or like you can drop the indexes and do all the changes to the database, and then you just say, okay, create index again, and it does the thing automatically, right? So you don't have to compute it manually or something, right? Good. Third kind of data, metadata. Metadata is data about data. So you want to know provenance information, you want to know the properties, you want to know the timeliness. Usually one very important metadata field is the timestamp. When was this data set entered, or when was this data item created, right? Very important to find out what happened to the data warehouse. Very important also to work with faulty situations, right? So consider you have a data warehouse, and every night you load the new data from the operational systems, and you need the night to do that, right? What happens if your server breaks down, or some like hard drive or something like that during the night, right? Do you do the complete extraction process and the complete loading process again? Or can you rely on that some of the data is already in there, right? You need timestamps. You need to know what happened when. And then you can set up a system that recovers at the correct point of time. And you can ensure that nothing is lost, but you don't perform work twice and three times and again, right? So it's sometimes difficult. Same goes for provenance and lineage. Provenance, lineage are kind of very similar concepts. It basically describes where data comes from. How trustworthy is it, right? Is that from just like simple stores, and might be wrong, like because the people at the cash register, when asked for their zip code or for their city that they're living in, say Greenland, or like some. I mean, who has not done that, right? MediaMarkt or Saturn are these typical examples that always ask for your zip code, right? Who says the right zip code? And who says 1, 2, 3, 4, 5, right? And that will end up in the data warehouse finally, right? So that's a little bit difficult, and you have to look very closely at the provenance. So there's definitely a distinction of data that has been directly input by the customers, that has been input by some clerks, and data where a first sanity check has already been performed, right? And you have to record these sanity checks. You have to see who looked at the data, who verified the data, and then you can if you know the lineage of the data item, you can look at the trustworthiness of the data item, the reliability, right? So for some operations, it might be only interesting to have reliable data. Then we have the presentation area, and the presentation area is where the data marts live. So data marts are views on the data warehouse, right? They are special focus areas of the data warehouse, where certain sections of your business, of your enterprise, right, or different departments have a different understanding of what they need. So, for example, human resources does not need product data. They do not need customer data. They just need the data from their employees, but they need that in a very detailed fashion, right? For the marketing department, the customer data is very important. They might even have employees as customers, but then they only need to know the addresses of the people or the names, like so, to recognize them, or a customer number or something like that. And not the full salary or the date of birth or something like that, right? That a human researches department definitely needs. So it's different data views, and like in relational databases where you define views to restrict the access to data very often, here you want to voluntarily restrict the data, not only for security reasons, so there's a little bit of data protection in there, sure, but also for the reasons of making it smaller, right? A data mart has a couple of terabytes, not petabytes, usually. The whole data warehouse has petabytes, right? So it's just difficult to work on the whole thing. And data mart is basically a materialized view of the complete data warehouse, right? So it's usually materialized, so it doesn't need to be computed times and again, right? It's computed once every night or something, right?
Does this mean this is another copy of your data?
Yes.
So you have your whole data in once, and then you have like 10 data marts where 1/10 of the data is copied, or more than 1/10 of the data.
Depends on what you need,
data
right?
mart is copied again.
A certain selection from your data.
So you need twice as much space, for example.
Probably not twice as much, but you will focus with data marts very often to some area where you say, okay, let's do a data mart that only has the data from this year or the last year, right?
Oh, okay.
Whereas in the data warehouse, you have 20 years back or something like that, right? And then you will go on and say, well, I don't need all the data, but most of the analytic queries are very short term, so let's keep a data mart, a separate data mart, right? That is very recent data. And the space problem is usually not the problem. The time problem is more the problem, right? So we have a strong tendency at the moment, a very, very strong trend towards, it's already called online analytical processing now, but they want real-time analytical processing these days, right? They don't want to do it online and then wait for an hour to get the query results, but they want to have it at their fingertips. They want to have the results or the statistics or tables or something like that as they talk, as they work with the data. And of course, over a petabyte size database, like where a normal query already runs 5 minutes, and then think about joins and think about shuffling all that data around, pre-aggregating or aggregating the data, doing group bys, it will cost a lot of time. So getting these clever snapshots for different applications, and taking a terabyte drive or 10 terabyte drive or something on top of what you have in terms of storage might well be worth the trouble, right? Because what's the deal? During the loading process, you just make one more copy. That doesn't kill you because it's a small amount of the data, right? You usually only append because you don't need to update, delete. You don't need to re-index most of the things. You just append all the data, right? So that's not too bad, and storage is cheap, basically quite reasonably priced at the moment. Right? But of course, there is talk about getting all your company database in main memory. So SAP, for example, is at the moment very big with the HANA database, which is a real time in-memory database that should store or should work on all the company data. And it just scales, like where we had, 1 gigabyte of main memory 10 years ago, and we're very happy about that. 1 gigabyte of main memory is not too much these days, right? So, good machines already have 10, 15 gigabytes of main memory, right? So, that's not a problem. Good. On these data marts, you can run the reporting tools, right, for the different departments, and specialized analytical processing tools that really work with data that the users need. And as far as the business community is concerned, this area basically is the warehouse. They don't care about all this big data store, you know, like all this big staging area and blah, blah, blah. They want the data mart. You know, they want their data prepared for them, prepared for what they're trying to do, right? This is business people. They don't care about what's under the hood. They just want the beautiful car, right? And to build the data mart, you need all that stuff before. You need a staging area. You need the operational system. You need the big data warehouse, right? But they don't care. They just want the data mart. Good. For the building of a complete data warehouse, you need to decide for the hardware, and you need a data flow architecture, because you move the data from the operational systems through the staging area into the data warehouse, into the data marts, and then you can work on it with the reporting tools, with the processing tools, right? So you have to model the complete data flow. You need to know what goes where, when, and how is it treated underway, right? And the most important step in that is the so-called extract, transform, load process. The extract, transform, load runs between the operational data stores, extracted into the staging area, transformed within the staging area, and loaded into the data warehouse. So the extract, transform, load process covers the first three columns of our basic architecture, right? After you decided for the hardware and the data flow, you have to decide for the storage structure. So how to store it. How do you want, what model do you want your data warehouse to follow? Do you want to build it on relational technology, right, with Oracle databases or something like that at the kernel? Can be done. Do you want to build it in a specialized model, in a multi-dimensional model? Can be done, right? But you have to decide for either one. You know, you have to go one way. And then you have to look into the data modeling. So how does the logical structure of your data warehouse look like, right? It's the same in relational databases. You decide on the hardware that you're going to use on the server. You decide on the software that you're going to use. I will do the Oracle, or I will do IBM's DB2 or MySQL database or whatever, right? And then I have to look at the logical design. I have to see how many tables do I have, what are the columns of the table, blah, 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 right? This is the same thing here. Hardware and data flow architecture, storage structure, data modeling. The only new thing is really this data flow architecture, right? Because in a normal database, the data just goes into the database and stays in the database, right? And here you have this flow from operational systems to the data warehouse. Good. If you look at the architectures that are used in practice, you will find that there are basically two different distinctions, and there are many hybrids between that. So we will see that there's vertical and horizontal partitioning systems, and there are some hybrids between them because both of them have their advantages, right? And you want to have all the advantages. You want to combine the advantages. You will find that very often in data warehousing, that there is the real canonic kind of good practice, right, or best practice, and then people mix it somehow to get the best of both worlds, and that happens very often. So you will find you will hardly ever find in practical data warehouses in big companies that they follow one and only one paradigm, right? But they will mix it, they will match it, there will be compromises, you know, like, and what comes out is kind of a living thing. So the first very popular architecture is vertical tiers, and there are two architectures for that: the generic two-tier architecture and the three-tier architecture. And it's like different layers of the data warehouse. So if you look at a two-tier architecture, you have the generic client-server architecture, where the server part deals with all the data preparation, with all the data storage, with all data transformation, right? And everything is done on the server side, right? And then you have the analysis that happens. And you have two possibilities. You can work with thin clients or you can work with fat clients. With thin clients, you would do also the processing here on the data mart. So the data mart does not only have to be storage systems, right? Storage area networks or something like that, NAS or SANs. But there have to be compute servers that actually do the computations. If you decide for a fat client, you would do the computations here and just access the data marts as external data sources, right? So you can decide for doing a lot of the computing here and having very heavy data transport here, right? Or you could do the computing here and have very limited data transport, only queries and result sets that are basically unchanged. Except the thin client architecture used to be the case, right? When we still have the mainframe, big mainframe architectures, thin clients used to be all the rage. Then we had a 20 years or something like that where we all relied on fat clients because the computers, the personal computers that everybody had at their office were amazingly powerful, right? And putting stress on the central system didn't seem to make sense. So you would do most in distributed fashions. Funny enough, we are back to thin clients again with all these mobile devices, right? So everybody wants it mobile now, and the business people want it on their iPad, right? And oh, look at my chart, right? And this is why most of the architectures are currently rebuilt into thin client architectures again. And you have specialized hardware. For example, IBM's NetTeaser is one of these very expensive but very powerful servers that is able to perform a lot of this data mining tasks and do it in a very nice and very quick fashion, right? So these are the two, basically two-tier architectures. Thin client operations are executed on the server. Client just used to display the result. And if you have the internet data warehousing access, if you want the mobility of the thing, right? You want to manage on the go, right? Then this is the right way to do it for you. Fat clients, server just delivers data from the data mart, and the operations are all done on the clients. You have a distributed computing environment. You can utilize the computing power of the clients very well, right? On the other hand, you have large data transfer, so you should have a very fast internet between them. So if your intranet is really quick, then there's no problem with shuffling around big amounts of data just for analysis purposes, right? If you have a weak internet connection, for example, via mobile devices, then it usually is not sensible to kind of copy complete tables or something like that around only for being aggregated on a thin client, right? So in intranet infrastructures, a fat client may be a good idea. In mobile infrastructures, a fat client is definitely a bad idea, right? At this time, one has to say, right? So it's evolving. We get faster mobile internet. We get stronger mobile devices, right? So probably there will be a trend where the cell phones of generation 9 or 10 in 20 years can perform the computations that our PCs are performing at the moment, right? So we have seen that happening, and it's not very prophetic to predict that it will go again into the area of fat clients, even over mobile internet. Then there's a three-tier vertical architecture. So in the first tier, you have the raw data, right? Everything that deals with the raw data. You have the operational data, you have the staging area where you clean and transform, and you have the data that is put into the data warehouse. And this is only ETL, right? This is the only process that runs in this area. And then on the second tier, you derive the summary data and the metadata. So you kind of work on the data in the data warehouse. You don't do that in the staging area anymore. The staging area is just for producing correct and workable raw data. Everything that is done here, the data marts, the summary data, the pre-aggregations, the materializations, is controlled in the second tier and is disconnected to the ETL process. This is very good, yes?
I don't know whether it's only a visualization of the architecture, but is it a good idea to separate the warehouse on two different tiers?
The warehouse itself is not separated, right? I mean, if you see this big box here, there is no big box. Well, never in data warehouse. It's all parts within the storage area networks that are somehow connected. So if you put the raw data in a different area than the metadata or the summary data, there's no problem because that is done anyway. You know, like this is just an integrated view in a way, right? But it's kind of the processes that is interesting. If you have some people working only on this tier, they are only interested in this part. They are not interested in what happens on the data mart side, right? They are not interested in that the transformation should prepare pre-aggregates, right? Or that the aggregation should already care which data marts are there or which data marts are not materialized, right? So you disconnect the processes of the actual usage of the data warehouse with the creation of the data warehouse.
Of course.
This is the idea.
Yeah, this is the idea. But wouldn't it be better if you, for example, do instead of 3 tiers, 4 tiers, so to say, well, the first step until staging area, you can put all these processes on one tier, and then the warehouse processes, which are maybe general, yeah, and close maybe relations, they can be on one tier and then the other tiers.
Basically, the idea which summary data exist depends on the queries that are coming in, right? You will definitely not materialize all the data summaries. That's exponential in space, right? If you kind of do all the groupings that are possible, it's exponential in space. You can't do that. You have to decide for one. How do you decide? Well, you know what queries are put. You know what data marts exist, right? And you prepare for those. So these things need to be together. Same goes for the ETL process. You can't stop here. You can't do ET because the loading is an integral part and the transformation has to prepare the data for the loading. Right? So the ETL process cannot be distributed really, right? The decision what to extract, how to transform it, depends on how you want to load it, right? The only thing you can distribute is after you loaded the raw data, what happens to the raw data? The ETL people can say, well, we delivered, so whatever you do with it depends on business purposes, you know, we don't care. You have all the data that you might ever need, right? And then the people here can focus on really the business cases and don't have to care on what's in there or what's not in there, right? So this is rather the administrative part of the data warehousing, right? The organizational part, and this is more the business part. This is more the how do you use it, what do you apply it for part, right? And then finally you have the client side, right? That is again thin clients, fat clients, like we know it, right? Good. There are other architectures, so you can have more tiers, you know, like you can break it down, But usually, the more tiers you have and the more tier interfaces you need, it increases complexity because, as I said, decoupling the ETL process, right, is very difficult because you can't transform data in the right way if you don't know about the schemas in the data warehouse, right? How do you want to transform it, right? You don't know what the result should look like. And then you have to have an interface that the logical design, whenever it's changed, tells the staging area, and that's kind of very difficult to do. Then there are web-based architectures. Very clever, of course, at the moment, because everybody's going mobile, everybody's going distributed, like you have these big data centers. So you want to have access to your data all the time, right? From all over the world, basically. We are in a globalized world. So with web-based architecture, you can reuse software and you have a certain kind of platform indicators because everything is moved into the cloud, that's one of the things you have to say to the enterprise people, to the business people, oh, everything's in the cloud and that's wonderful, right? They will love that. On the other hand, disadvantage, you definitely have a security overhead because the company data is one of the biggest assets of the company, right? It's what is very valuable to the company. Putting it in some cloud, right, and making it accessible for everybody everywhere, right, can be very dangerous, can be very difficult. And you have to have a lot of encryption, user access, identification of users, credentials, blah, 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 which creates a lot of overhead as opposed to your intranet, where you say, well, there's a firewall to the outside, right, and what happens inside is probably okay, right, and once it gets to the outside, that's a big no-go, right? Here in web-based architectures, you really have to deal with these issues. You really have to find out what it's all about. Good. Vertical tiers, right? Horizontal tiers. You can also partition your data warehouse in horizontal parts. There's basically three models: the independent data mart, the dependent data mart, and the logical data mart. And the idea of these data marts, of these horizontal partitions, is that you build not one big data warehouse where all the company data for all further processing and all further administration and reporting and analysis is stored, but that the complete data flow process from the operational system to the data mart is built with respect to the use of the data, right? So for some data marts, you might need a very complicated ETL process, you might need to do a lot of cleaning, you might need to do a lot of whatever, right? For others, you need real-time data, very fast loading, but the data does not have to be clean, right? So you can afford to have a little bit of noise in there, right? So having a different ETL process for those different application scenarios might be a very good idea. So you don't partition vertically, but you partition horizontally, depending on the data mart that you're looking at, right? So every data mart has its own ETL process. Yes?
In this case, this would mean that you don't have all the data, right?
You don't have a central data warehouse anymore.
You said earlier that the data marts are only for a certain time stamp, so last year or something. So that this would mean that
depends on how you define your data mart,
But here it would be possible that you lose data, that you will delete data.
You don't delete data. You just decide which data to keep or not. Right? And if you say, okay, I'm a stock market analyst, right, or I'm a day trading broker, I don't need a year-old data of the stock market, but I need it in real time. I need it in the millisecond, right? than building an architecture that first tries to integrate the new incoming data into your big data warehouse centrally, pre-aggregation, blah, 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 and then delivers it to your data mart is killing you, right? So what you basically do is you say, well, I directly shift it into the data mart, and everything that is older than a day or two is just thrown out, right? And of course, you can also say, well, I might have both possibilities, right? I might have both, I might need both, right? For the day trading, I need the real-time data really directly done. But I still need the trend analysis of a stock, right? I need the year or 3-year total movement of the stock, so I can do trend channels or whatnot, right? And what would you do in a vertical architecture? You would have one data mart for the day trading, and you would have one data mart for the trend analysis. They would have independent ETL processes. The one would just move the data through in a very fast fashion and do not care about old data and total data correctness or something. The other one would kind of work on the data, integrate it, and store it long-term in your trend analysis warehouse, right? So since the data mart are duplicating data anyway, you know, that would not be a problem. But the idea is that the data flow adapts itself to the usage of the data. And you might have different data flows for different usages. And they coexist in different horizontal layers. This is the idea of horizontal partitioning, right? Good. So if you have independent data marts, they don't know anything of each other. They're just mini warehouses, limited in scope, limited in what they do, and have their own processes, right? This is kind of the idea. And of course, you have separate ETL processes for each data mart, and you do a lot of work twice, or 3 times, or 4 times, right? Depending on how many data marts you have. So that's kind of the difficulty of independent data marts. You might have dependent data marts where you say, well, basically, let's do a single ETL for the data warehouse, so we don't have the redundancy in the ETL process. But then the data marts are directly loaded from the data warehouse in different fashions, right? So that would be dependent data marts that share a ETL process. The problem with that is, what's the problem with the dependent data mart? What's the disadvantage? Well, different requirements of the data marts cannot be reflected in the ETL process. The ETL process has to reflect the strictest requirements and nothing else. Everything where you could say, oh, I don't need this data cleaned thoroughly, right? But I need it faster. That doesn't work. Because you will get it once it's cleaned because some of your data mart needs it cleaned. Right? And that's just a single ETL process. So, depends on advantage, disadvantage, right? Good. Then you have the logical data mart. The logical data mart is an idea. You don't split the different data marts, and these are the horizontal tiers, but you split the data in the data warehouse and build horizontal tiers with it. So there are logical views of the data warehouse, and which give you basically an integrated view of the enterprise. So if you really can separate it and can say, well, I have the data warehouse, you know, it keeps all the data about the employees and the customer and the product, but you know, like they're rather independent of each other, right? Then I can directly layer the warehouse and just say, you know, like let's use different partitions for that in the data warehouse. And this is kind of the idea of logical data. The data marts don't exist anymore, but are just logical partitions of the data warehouse. Right? That's how it works. No. Okay. So data warehouses versus data marts. In the scope, the data warehouse is application independent, centralized, and planned. The data marts are built for a specific application. They are decentralized by nature, and they are probably planned, but they evolve as the application evolves. Same for the data. Data warehouse contains everything. Data marts only a fraction of the data, only what you really need. Data warehouse is usually lightly denormalized because you can't denormalize everything. That would be exponential in storage space. Data marts are usually highly denormalized, so everything that can be pre-computed for the application is pre-computed. And since you have left data, the storage explosion is not so bad. Subjects, data warehouse caters for all the subjects that you have in your company, right? So you can build all the analytical processing that you want. Data marts, only one central subject, only human resources department, or only whatever, right? Sources, internal, external sources, everything for the data warehouse. Only selected ones for the data marts, whatever you need. Other characteristics. Data warehouses are flexible, data-oriented, long-life, large, and single complex structures. On the other hand, data marts are restrictive, project-oriented, short-life, start small, may become large after time if they're used constantly. You have a lot of distributed structures, which is, however, in itself easier to maintain. So the structure itself is probably more complex than the integrated data warehouse, the distributed structure, right? But each part of this distributed structure is simpler than the data warehouse. So decide what you need, right? From a user's point of view, it's usually good to have control over your own data, so you want it as decentralized as possible. From the data manager or CIO's point of view, you want it as integrated as possible, so that the data is consistent and the data can be integrated in a reasonable way. Cool? Data warehousing, data marts, clear concepts? Right? Good. Okay. So, as I just said, centralized versus distributed. A central database is usually if you have a big company and that is very focused, also locally focused. Typical example are Volkswagen. They don't call their data warehouse, but they call it Gravitationszentren, which sounds funny sometimes, but it's like where the data gravitates to. So that was the basic idea. I don't know if it's a good metaphor, but anyway. But the one thing about Volkswagen that everybody knows is that the heart of Volkswagen is in Wolfsburg, right? And only in Wolfsburg. So they do have a lot of factories around. They do have a lot of subsidiaries, but they don't care about that. Everything that is of meaning, everything that is strategic, everything that is done, with long-running management goals in mind, is done in Wolfsburg. So they have a central data warehouse where all the data from the different facilities flows in, right? And then they just have their compute center and they work with the data in that way. For the distributed data warehouse, typical case is Walmart. Walmart has a lot of locations. They have a lot of stores. And these stores are kind of independently responsible for what they do, for what they keep in stocks, for how well they do their selling, how they do management, how they do a lot of the marketing promotion campaigns and stuff like that. So they need the data at their hands, and they only need their data. They only need a view on the other data, but not really the very highly resolute. They don't need the data of the whole company in a higher resolution. They need the basic data of the company and their data in a high resolution, right? Their store data in a high resolution. So if you have globalized companies that are very distributed, where the management is not like Volkswagen, right, where you really have this kind of very central government, but you rather have a central administration, and everything is done in decentralized fashion anyway, then it's better to have a distributed warehouse, right?
Are there some connection between the maybe different locations?
Sure, there are
Does
connections.
it depends on the enterprise?
Well, it depends on what business model you have behind. So there are, for example, franchise operations, right, where each store is independent of the rest. They just share a common administrative infrastructure and a common way of doing things, right? So what do you care about how one company that does a lot of franchising is, for example, Starbucks or the McDonald's or something like that, right? They're not under central management. So what should the Braunschweig McDonald's care about the data from the Munich McDonald's, right? It's not comparable. They might need something like, okay, how does the usual McDonald's do? You know, like, or are we below profile, or are we doing well, right? And how is it with, I don't know, cities with 250,000 inhabitants or something like that? How do other McDonald's in these areas do, right? Prime location or outskirts or I don't know, right? But you only need aggregate data of these other people. And it depends on the business model. So Volkswagen, for example, has a very centralized business model. Everything goes via the desks in Wolfsburg. You know, every single decision. So they need the analytics to be there.
Because we mentioned before in relation to the cloud.
Yes.
For example, if we put our data in the cloud, then one of the disadvantages is the security, data security, and so on. And in this case, if we have different hardware and software locations, it might be also kind of.
It is a disadvantage, definitely. But usually, if you build a data warehouse, for example, in franchising organizations, you don't allow direct access. You will only allow access to other distributed locations via the central location. And they will ask for the data and then hand it on to you. Right? So the security is kind of managed. Right? Right. Good. Okay. Then you have distributed data warehouses, and distributed data warehouse may be geographically distributed, technologically distributed, or independently evolving, which is kind of the horror story for all the IT departments and companies. But let's look at it. So talking about distributed data warehouses, we can first say, okay, many companies are globalized these days. It's not just they have one location and they work on that location, so it's clear where the data is, but they have different locations, they have different countries they are active in. And once the cooperation spreads around the world, also the data is produced in different areas of the world. So then you need a certain idea of the local information that needs in a very fine detail, in a small grained resolution, and you need the global information where you probably need a coarser resolution for the data. So building a distributed data warehouse makes sense when much of the processing occurs on the local level. So when you really have to work with the small data, day to day, so what's in stock and what has been sold and so on, right? Also when you have business models that make the branches autonomous. So if you have a franchising business model, right, there's no way you would share all the data that you have with other branches, right? You don't do that. You don't want them to know how well you do or how bad you do. You know, it's none of their business, right? So that's kind of the idea here. Typical example, McDonald's franchising, right? If you have the data warehouse in Asia and the data warehouse in the USA, they collect the data from the different stores, from the different facilities, but they only exchange aggregate data. They don't exchange the raw data, and they don't allow access to the raw data. So if you want something very specific, you have to ask the other side. Good. Technologically distributed web data warehouse is kind of pushing the distribution and all the security and encryption and blah, blah, blah process to the vendor, right? So what you want is you want a central data warehouse, and it should feel like a central data warehouse, but in reality it should be high availability, it should be elastic and so on, right? It should be distributed. This is typical example of cloud data warehouses, right? So I don't care how the cloud works. I just ask Amazon to do it, right? And I don't know on what servers my data resides, or I don't know how well it is backed up, right? I don't care, but it should not fail, and it should be always available 24/7. And if it isn't, I will kick Amazon's ass, right? But I'm not responsible for that. This is the idea of technological distribution. So the advantage is, the real advantage for that is that you first can build these nice web kind of style architectures, which is very modern these days, especially for mobile applications. And on the other hand, the idea is elasticity. Elasticity means that your hardware and your infrastructure grows as you grow, right? So if I have a small company, right, I cannot invest in all the servers that I might need if my company becomes a world-leading marketing firm or something like that, right? I just have a single server. And as soon as the customers are coming in, I need to decide, oh my God, I need more storage space, I need more computing facilities, right? And I have to build with that, right? What am I doing? Am I investing in a compute center, or am I building it server by server, right? Which is very expensive. I don't want to care about them. That's the idea of elasticity. So I ask Amazon to handle that for me and basically say, the more requests come in and the more customers are there, the more you can charge me. But I won't care about how many servers you have or where they are, or like how they're supported or whatever, right? This is your business. And they're kind of interesting idea. Good. So on the other hand, if you have this cloud idea, if you have this elastic idea, the communication is kind of the important factor, because cloud means that you have to upload it into the cloud, and then you have, whenever you do analysis and stuff, you have to download everything from the cloud, right? And depending on the connections, that can be by far slower than intranet that is coupled with your enterprise architecture, right? So consider we have 4 nodes, each having the data for a specific year, and if you now consider a query which needs to access all the data from the different years, right, and do a join with them, then you have to ship it into a single place, right, to do the join. That can be very expensive, that can be very time-consuming. Then there's the third, the horror, and that is independently evolving distributed data warehouses. And that happens very often in organizations if they don't have a central CIO that looks at the architecture. I was talking to some guy from a really big IT department of a company, of a global company, and he says they currently have 4,000 different softwares in practical application in the company. And of 3,000 of those, he does not even know what they do, right? And the only way to find out is to take it offline and then see who yells at you, right? So this is kind of very difficult. So I don't know, customer management decides they need new data, they want the age data of all the customers or something, and they're getting it somehow, right? and they're putting it somehow in their data warehouse. You can guess what happens, right? Nobody knows about that. It's not integrated. It's not cleaned. It's the horror, right? And yeah, it's kind of all these legacy systems that you have to integrate. It's just not worth the effort. But sadly enough, if you're working in data warehousing, in some time this is what you see in most companies. So there's usually not a central kind of idea behind it, but it's usually independently involving distributed data warehouses. Good. Then I would say we make a break. Is that?
Let's go on with the lecture. So this is the first deco for today, and the only deco for today. And I will talk a little bit about data storage and what it means for the data warehousing for partitioning schemes that we have. So data storage is basically performed in such a way that it helps the applications, right? So you store the data such that it's persistent and secure and blah, blah, blah and everything, right? But you have different possibilities how you store the data and where you store the data and how you kind of connect the data, what partitions do you use. And in relational databases, this is kind of called physical tuning. So you go down to disk level basically and look at what data is commonly accessed together. So you want a sequential read on that, and so on and so on, right? And the same applies to data warehousing. Only that here the idea is that basically you need to store the data in such a way that it aids data mining, data analysis, reporting tasks, right? So this is different kinds of queries, right? This is special. So what happens here basically should reflect on how it is stored here, right? This is the basic idea. Good. And if you take the users of data warehouse, they're usually departments of human resources, enterprise resource planning, marketing or something like that. So department or specialized tasks that need to access the data in a specific way. So they usually have a certain perspective on data. They look at it from a time perspective, from a location perspective, everything that happens in a single store or something. From a product perspective, so for example, marketing for certain products, how does it sell, where does it sell good, where does it sell bad, and so on. And these perspectives are called in data warehousing dimensions, right? So it's an aspect of the data, it's a dimension of the data. And thus, since the different departments have different dimensions, have different perspectives on the data needs to be multidimensional. It needs to cater for all these different dimensions. And as you can imagine, that's rather hard to do on a disk, right? Because a disk is not multidimensional. So you kind of have to build a mapping between this multidimensional idea of storage and the real underlying storage structure and how you do that, right? So multidimensional means that, I don't know, if you take a car manufacturer, for example, and the sales department, they need to know about sales volume, right? And they might order the data in different perspectives, right? They might look at different volumes by model. They might look at different colors or how different dealers did, or different locations, right? Was one type of car more often sold in a certain country, or did it not sell well in a different country? Maybe the naming was wrong, or maybe the color range was not what the people expected, or whatever, right? To find out these things, they need to group the data, they need to manage the data in such a way that these different dimensions are reflected, right? And what happens is that you get a multidimensional structure very soon. So for example, you might have the different models or the different colors of your car. So a car model might be coupe or sedan, minivan, right? And then you have different numbers of sales for that, for the different colors, right? Black, blue, red, or something. One specialty is kind of the star, so every color, so this is basically the sum of all these. Right? This is basically the idea that you just take the sum of everything, all the colors. This is star, right? And then you break it down in red, blue, black. All the models again is star, and then you break it down in minivan, sedan, coupe. So this is also just the sum again of the whole number. And in data warehousing talk, you call these things dimensions, right? Because they're different views, they're different data accesses. And you call these things measures, right? Because you measure something. You measure how often something was sold, or what was the price, or what was the revenue that you created with that, or something like that, right? You measure something, so it's called a measure. And you see that it's very easy with this table to answer queries like, okay, how many blue minivans were sold, right? Suck. I know it immediately, right? As opposed to how many minivans were sold. Suck. I know it immediately. Sorry. Minivans suck. Right? Yeah? All colors. So the idea is that all the values that I need for answering queries are there. They are pre-computed. And all the information is in that table, easily accessible for me. On the other hand, this table is two-dimensional, right? Now I still have a time dimension, I still have a location dimension, I still have different dealers, I still have blah, 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 right? You can imagine you get a lot of dimensions, and it's not going to be the spreadsheet, it's not going to be two-dimensional, but it's going to be multi-dimensional, right? So if you take something more, so for example, the dealer, you add a new dimension, making the spreadsheet into a cube, right? 4-dimensional cube, 5-dimensional cube, 6-dimensional, and so on and so on and so on, right? It gets higher dimensional, and the number of positions, the number of measures in it explodes, right? This is the basic idea behind it. So when you have 3 dimensions with 10 value each, you get this huge block, right? Before you have the spreadsheet. And the more information is in the data warehouse, the bigger this block will be. And you really have to cater for different ways of doing it. The visualization is, of course, also multidimensional, right? Because you need to know what dealer in what country did what, or sold how many issues, right? You got several dimensions in almost every query. On the other hand, you have the operational data coming from the operational databases, from the OLTP databases, usually in tabular form, right? There's a mismatch. Right? You have table data from normal relational databases, and you want multi-dimensional data for the analysis, for the queries. It doesn't go together. You have to do something in between. You have to let something happen, right? The interesting thing is, if you look at the relational model and the multidimensional model, you will find out that the database manipulations that are possible in the relational model are also possible in the multidimensional model, and vice versa. Right? It's kind of the same thing. Those technologies can do it. It's only a matter of how efficiently they can do it. Right? We saw the analytical query that Walmart ran in the last lecture. Right? The 6 or 7-way join query. Took like hours to execute on relational technology. Works very quickly on multidimensional technology. On the other hand, updating database works very quickly on tabular data. Very annoying in multidimensional data where you have to cater for all the aggregates. So depends. So in the context of data warehouse, the multidimensional model has advantages in presentation, mainly performance, definitely, right? You can't do OLTP with it. If you go into high throughput transaction processing, multidimensional just has too high overhead. On the other hand, the overhead is kind of, the overhead is kind of the idea of why it speeds up the queries, right? Because things are pre-aggregated, things are prepared for you. So in the multidimensional model, the presentation is natural output, because you just take the measure that you need. Relational model, 7-way query, terrible, right? Hard to write, hard to maintain, hard to check for correctness, takes very long to execute. Good. On the other hand, multidimensional model, when new data is added to the data warehouse, aggregates need to be maintained, right? Additional time. Relational model, on the other hand, uses indexes, sophisticated joins, which also require some maintenance, especially if you do materialized joins and stuff like that, or materialized views. But of course, you have to build your data warehouse on something. You know, you basically have to break it down to disk at some point. So you can always claim, yeah, this is multidimensional data model, but in the end, your disk is not multidimensional. Your disk is one-dimensional, right? So you have to decide how to store it. So if you store it in the data warehouse according to the relational model, then so basically tabular data here can be done. Then for every query, there has to be a transformation from the relational model to the multidimensional representation. If you try to build a multidimensional model in the data warehouse, the transformation happens here during the load process, right? Where do you want it to happen? Do you rather want it to happen during the load, making a longer load but easy query? Or do you want to happen for each query but short load times? Well, it depends on your application, depends on what you're trying to do, right? If you do a good database tuning, it has been shown that with the relational model, you can reach similar performance as the multidimensional model. But of course, it's not possible to tune in advance for all ad hoc queries. You can only tune for queries that you know they're coming. So if you have a lot of repeating queries, of repetitive queries, you have a lot of queries of different views on the data, grouped by location or grouped by product or something like that, that you know they are coming, you can tune the database into that direction. On the other hand, then, if a group by time query comes, you have to perform it right. You have to compute it. It takes a lot of time, but your database just is not prepared for it. And you can't prepare a database for all the different kinds of queries because it reflects on which indexes you build and how you store the data sequentially on disk. Right? So basically the binary in. So the conclusion here is that you can basically use both models. That's not a problem. You know, like you can do relational or you can do multidimensional model. But due to rather invest a little bit more in the load process and then have easy querying and have quick querying, that is rather reflected in the multidimensional model. So having a native multidimensional model in the data warehouse for storage is probably a good idea. Now, of course, as I already said, well, the disk is not multidimensional, right? So you now have to break down the multidimensional model that you use as a data visualization or data aggregation paradigm in the data warehouse has to be broken down to disk, right? Of course, this has to be done for the relational model too. And that goes back to data modeling. And
if you remember the lecture on relational databases, we had this ER scheme modeling, right, where we just went into, okay, you have the entity, right, and E1, and then you have a relationship like that to E2, right, and this is relationship R or something like that, right, and you model with that, and then you can directly build it into a table structure, right. This is basically a logical database modeling. And that worked quite well. So the data model has a certain definition and defines the format of the data. It defines a class structure, if you want, like that, right? And with the good idea about the ER modeling was that it has a very, very easy to understand and very easy to comprehend graphical representation. So you will find that even non-expert, non-database experts very quickly get the drift of what you're saying if you show them the ER model, and they can argue with you, okay, wouldn't you need this data here, or wouldn't you need to do it in a slightly different way, right? So you basically have different areas of interest there. You have the enterprise data model, which is basically the integrated data of your whole enterprise, and you have subject area data models that cater for certain departments, that cater for certain applications, right? And you can define that. If you look at what we did in relational databases, we had this modeling process basically layered in two types. The one is the pure modeling on a theoretical scale, right? This is the one up here. This is DBM is independent, and then we had to break it down to the implementation of the database. This is the one down here, right? So what you would do basically on a theoretical level is first the requirements analysis, where you find out what the users actually want and what functionalities they need, and that would go into a conceptual design, which can be broken down into logical design. And then if you decide for the relational database model, for example, you know the logical design includes table, so it's kind of mixed between the database independent and dependent scheme. But you have all the information that you need, you have all the design that you need. Now comes the interesting point, right? For the applications, for the users, you need to build, you need to design the applications that they work on, maybe a reporting tool, maybe a data mining tool, you know, transactions, well, questionable in databases if you need that, and then you get out the applications, right, and that's that. That's for the user level, that's for the presentation level. The interesting step is here, right? Because this is where storage comes into the game. This is kind of where the underlying database model very strictly defines how you get your data on disk. So for example, if you use a relational data model and you put a primary index on some attribute, then the tuples will be stored according to the order introduced by this primary index on disk, such that you can do a linear scan, a very efficient, a very cheap linear scan over the data following the primary index. Depending on what you chose as a primary index, some queries will run very fast because they can benefit from the linear scan. Some will run very slow because they use a different attribute, you know, like that is somehow scattered over the disk, and you need to reposition the reading head all the time, right? And this is kind of the interesting part, especially here, because depending on what database management system or basic management system for the data warehouse you chose, this mapping has to be done, right? So the phases are basically the conceptual design. You look at all the different items that you have, all the data that you need to extract from the sources, which is rather high level, right? Then you have the logical design. We will talk next week about the actual logical design. So how do you do tables, or actually the question is rather, do you do tables in data warehouse, or do you use something else, right? We will talk about that and discuss that in the next lecture. So logical design will be next lecture. It can be relational model, can be multi-dimensional model, and so on. This should read multi-dimensional model. In any case, it is adapted to the software that you're using. And then also in the next lecture, we will talk about the physical design, right? And physical design means that you need to create access paths, that you need to create indexes, and so on. And we'll talk about that next week too. Good. So you move between the phases. So you start with the conceptual design. You build your ER diagram, like you go to the logical design, you break it down to table columns, you go into the physical design, you create the access path, and so on, right? And basically, once you have performed this, and that is the beauty of the design, those things here are rather automatically, right? This can be done with default parameters by the databases themselves, right? And so this is kind of the wonderful thing. In the conceptual model, you just have the conceptual ideas, you have the conceptual grouping of ideas, and if you have similar categories, you will find the data usually clusters around these categories. So if you're looking at a university database, there will definitely be a concept of students, and you immediately know what attributes students should have. So they have an immatriculation number, they have a name, they have a home address, they might have a semester address and a home address that are different. You know the characteristics, so you can model them in a way that they reflect the real object quite sufficiently for what you're trying to do with it, right? And then you, of course, have to define the major relationships, and they are also given by the idea of being a student. So a student should listen into lectures, a student should take exams. So you need all kinds of relationships that connect students to these activities, right? So you know what to model, and you have very low or something like that. We use in relational databases usually entity relationship modeling, and I will show you how to build it up for the data warehouse, for the multidimensional idea in just a minute. There's also multidimensional entity relationship, and the idea behind that is that the entities reflect the things in the world, a student, a professor, a lecturer, or something like that, right? And the attributes are just characteristics. They are just properties of the entity. So a student has a name or an immatriculation number or an address or something like that. Lecturer does not have an address. The lecturer does have a lecture hall, for example, assigned to it, right? Or a name or whatever. And the relationships are kind of relationships between different entities, so that allow the entities to interact. So a student can visit a lecturer, or a student can take an exam or something like that, and these have to be modeled somehow. And then you get this kind of very complex image of conceptual models and how you do it, right? This is what we basically did in relational databases 1. The conceptual design is mostly done in ER, but nowadays ER has become a standard part of UML. So kind of same thing, but somehow unified. So the unified modeling language has different different names for the same concepts. So the entity becomes a class, and then you can do some more. You can do packet diagrams, or you can do sequence diagrams and so on. So you can express a certain behavior in a certain kind. So UML is a little bit more extensive and somehow more expressive than pure ER, but the basic ideas go back to ER, so that's kind of same idea. For the data modeling, you usually have this class structure where you can inherit, or where you have the class that has attributes and so on, and you skip the operations, you skip the behavioral part of the classes, and then you have associations between the classes, which are basically the relationship between entities. In the logical model, you arrange the data into logical structures, right? So the idea of a logical structure is you have a certain relation in the relational model, for example, where every tuple is a row in the relation and every attribute is a column in the relation, and then you just take the values that are for a certain attribute in a certain tuple, and you can combine all this information, right? Depending on the model that you use, you have different structures. So, for example, the table is very common for the relational model, or is paramount for the relational model. In object-oriented databases, you would have object structures. In network databases, you would have a path to information. So you would have basically the different paths that lead to the attribute or the value that you're looking at. So it can be different structures depending on the model that you use and depending on the database that you use. Finally, the physical design. This specifies the physical configuration of the database, and this is really related to the disk. This is really hardware level, right? How do you put the data? How do you or how do you allocate the data such that you get the best benefit from sequential reads? Do you replicate data? Do you put indexes or primary, secondary indexes on certain attributes, and so on, right? So this is kind of the idea, and you usually have a so-called data dictionary that tells you something about the configuration of a database, that tells you something about what tables are there, what indexes are there, and so on. So you can use it in applications. Good. For the data warehouse, you have to model multidimensionally, as we said, right? And multidimensional is kind of almost opposed to the classical relational model. Because if you remember RDB, what we always tried to do was normalization. We tried to minimize redundancy. We wanted to take less space, and compactify things. We were talking about consistency. We were talking about a lot of issues, transaction support, and so on, that do not really fit into the data warehousing world, because consistency, yes, is okay and it's nice, but what's the sacrifice you do for it? If I have slow queries because I have a very high consistency, right, then sacrificing some of the consistency may be okay, right? Then one sale is wrong, so what, right? It does not really depend on the individual row. It doesn't really depend on the individual tuple, right? But it's the massive amount of tuple that matters here. So what we do is not remove redundancy and allow the efficient retrieval of individual records, but we say redundancy is necessary to speed up access, right? So we want redundancy, we need redundancy, and we only focus on multiple tuples. So we want all the sales in one location, like we don't want the individual sales. We couldn't care less about the individual customer. We want the customers who do something. We want user groups. We want all kind of aggregations of data. We are interested in the broad picture, right? Not in the individual item. So RDB is basically individual item. And is optimized for that. Data warehousing is big picture. And is optimized for that, right? This is the idea that we have. So if you look at the business queries, we were talking about the different subjects. So we said that data warehouse is subject-oriented, which means that the subject should be the prime kind of citizen in our model, right? If I focus on the product, then everything should be centered around product, right? There should be different product families that we can aggregate. The product should be measured by how often is it produced, you know, like, or in what different variations is it done, or how can it be parameterized, or whatever, right? So you can define on all the different questions of interest depending on your business model, basically, you know. So if you want to question who buys products and you want to do targeted marketing and stuff like that, you should do a subject orientation on the customer, right? If you want to talk about your dealers, if you want to look at or organize and optimize your dealer network, you should talk about the location of stores, dealers, something as the subject. You might talk about the structure of the products, you know, what was sold. You might talk about time, when was what sold, so how are you doing over time? Are there possibilities to optimize that, right? And depending on the business model, you have all these different views, right? And what you're interested in is the subject that you orient your data warehouse on, right? So for the conceptual design of a data warehouse, you first need facts, and facts are the subjects, right? This is what it's all about. Sales, shipments, orders, customers, whatever, right? Whatever you are interested in, this is a fact. Then you have the measures. The measures are the values with which you measure the fact. How many things did you sell? What revenue did each sale create? Taxes, I don't know, right? So everything that can be measured with respect to the subject that you're interested in, with respect to the fact that you're interested in. Or if you look at a customer, you know, how often does he shop in your stores? How much money does he usually spend on average in the store, and so on, right? So all the information that you want to have. Then you need to figure out the dimensions that you're interested in, the product, the time, the location, the whatever, right? Whatever you're interested in, dimensions. And within each dimension, you need to figure out the hierarchies. You need to figure out, okay, is time really granular on the second, or do I need daily, weekly, monthly, per year, or something like that? So what granularity do I want to have, and do I support multiple granularities? So different queries might focus on, you know, like the yearly behavior of something, or the weekly behavior of something, short-term versus long-term prediction, right? But these are the four things that you have to be aware of and that you have to decide for based on your enterprise model. The facts, what you are interested in, hierarchies within each dimension, what's the granularity, what's the coarseness of the granularity that you're looking at. Good. There are basically a couple of conceptual design models. One is a simple extension of the entity relationship model, which is called multidimensional entity relationship, or MER modeling. Clever. There's also multidimensional UML modeling, same thing, basically works in the same way. And there are other methods, the dimension fact model, TOTOC, and so on. You will find a lot of different paradigms and a lot of different architectures around that. I want to go into the first two, the multidimensional ER and the multidimensional UML, and they're very similar to each other anyway. So the idea of multidimensional ER model is that you get an intuitive representation of the multidimensionality of the data, right, that you can share with other people, especially with users. So when you talk about requirements, when you talk about doing the conceptual design of a database, you have to reflect that what you are doing is what the users really want to use in the end, right? And so you need a certain representation, you need a usually graphical representation to show them, okay, this is what I intend to implement, right? And then they go, okay, this is what I need here, I would need some more, or I don't need that over here, or something like that. And then you can decide and work out with them what the things are good for, or what else is needed, or what changes are needed, and so on, right? So this is kind of a specification of the multidimensional semantics of what you're trying to do. And semantics is always something that is dependent on what you want to do with it in the end, right? So you have to talk to the user, you have to talk to the business analyst and see what they need. The notation of multidimensional ER model was basically influenced such that it was a specialization of the ER model, so it should be used together with normal ER models and just extended wherever needed, right? And thus it has the full expression features and the full power of the ER models, and can be kind of transformed into a logical model automatically, like the ER model is, and you only need to care for the specialized features that you added to the ER model, right? And build certain mappings for them, and then the automatic building into logical design is still valid. So this was the basic idea, right? It should of course be a minimal expansion, because if you duplicate ideas from the ER model with the same ideas or roughly the same ideas from the multidimensional model, right? Then you gain nothing. You just have confusion on the user side how to model something. If there are two ways to model the same idea, there might be a certain physical difference in how it is actually built into a logical model, right? The user doesn't know about that. The modeler doesn't know about that, and this is kind of difficult. So the number of additional elements should be as small as possible. And then you have the representation of the multidimensional semantics. So that is kind of the interesting point. Minimal expansion, minimal specialization, but it should reflect the multidimensionality of the model, right? And the full multidimensionality. So the question is, what do we need? There are basically three constructs in multidimensional ER. One is the fact node. One is the aggregation level node, and then you have a special binary classification edge. We will come to that in a minute. So let's look at a store scenario that you design in ER. You might have an article, and an article is sold in a store. The store is located in a city. And you have all these different tuples over there, right? This is typical relational schema. And you can say, okay, which article was sold in which city? But you need a join, right? Over here and over here, right? To get it across. Moreover, the ER model cannot really state something like, okay, a store is in a city, the city is in a certain country, so I want to group by countries. But you would have to look up all the cities of a country and then kind of find out which belong to the same country and do a grouping by that, right? Something like where city is in, and then a list of the cities of the country or something like that, right? Expensive operation. You don't want that. You don't want that. So what you could do in multidimensional ER is that you basically say, okay, I will look at sales. Sales is my subject orientation. And I have a certain number of characteristics. These are the measures of sales. I want to measure sales by the quantity. How often was something? So how many items of some product were bought, right? The price, the revenue that I created, the taxes that I took. All valid measures that go well with sales, right? And then you need the dimensions. And for each dimension, you add an edge to the fact node, right? And you said, well, this fact node has 3 dimensions. One dimension has to do with the product, one dimension has to do with the location, and one dimension has to do with the time, right? You can add more if you want to, doesn't really matter. You're multidimensional, right? This would be 3-dimensional in that case. And now comes the special binary classification edge, right? This is not a relationship between something, so the sales are not in relation they are in relation to the product. Let's write that as product. This is location, and this is time. And as you can see here, these edges are normal edges, right? So they are normal association. A sale is associated with a certain product, it's associated with a certain location, it's associated with a certain time, right? But within the dimensions, there's the idea of granularity. So a certain article on your shopping list belongs to a certain product group. And this product group belongs to a certain product family. And this product family belongs to a certain product category, right? Or do the same with location. You buy your article in a certain store. The store is in a certain city. The city is in a certain district. The district is in a certain region. The region is in a certain country, right? And you build these classification hierarchies by using these binary classification edges. And they just have this little split arrow at the end to show these are not associations, right? Not normal associations, but they are classifications within a hierarchy. And you just roll up, you just kind of aggregate over that. So country consists of all the regions in the country. So Bavaria or Lower Saxony or whatever, right? And the district or the region consists of all the districts. So Lower Saxony is made up of Braunschweig, Hannover, Oldenburg, and I don't know the others, right? And within each district, there's a certain number of cities. So Braunschweig has Wolfenbüttel and Wolfsburg and Braunschweig and Beine and I don't know, right? And within the city, there are one or more stores. So you have, I don't know how many McDonald's stores you have in Braunschweig, but there's one in the city center and one in the industrial area and one in Weststadt or I don't know, right? So this is kind of this idea of the notation behind that. So the sales was selected as a fact node, and it has 3 dimensions that are associated with it, right? Normal association edges, right? Product, geographical area or location, and time. Dimensions are always associated on the lowest level. So for the product, it's the individual article that you sold. For the location, it's the individual store. And you cannot go below that. So if I know it was sold in a certain store, I don't know on what floor in that store it was sold, right? Or what the product that somebody buys consists of. But I have to define a lowest level of granularity that I want to query, right? And there's no lower than that. But on the other hand, I can define a certain level, right? So the articles can belong to a product group can belong to a certain family or something like that. So somebody bought a, I don't know, computer, and computer is in the product group consumer electronics or something like that, right? And then you just go up and make bigger groups of that. The dimensions are represented through the basic classification level. Those are those. And there may also be alternative parts in the classification level. So the classification level has a certain granularity. So I don't know, day is part of a month is part of a year is part of a decade or something like that, right? Everything that you need. But you could also say something like day belongs to a certain week and to a certain month. So the week does not belong to a month, not necessarily. It can span 2 months, basically, right? So you can have alternative paths in these classification edges. That's not a problem. And this, yes?
I have a question regarding the alternative paths. Well,
yes.
you had on the slide before, you had a region and a location, and I thought of the fact of the possibility of joining these paths.
Yes.
Well, a store might be in a certain zip code,
yes.
And the zip code might span 2 districts, for example. And with weeks this doesn't work, but a zip code always belongs to a certain country.
Yes.
Is it possible to join these paths at the end, or even?
Yeah, sure.
Okay. Sure. How would I annotate that?
You could also say, well, with weak it doesn't really work, right? But if you have, I don't know, the city is in a certain country, it's in a certain district. Are there cities between districts?
I don't know, but that's why I chose the example of a zip code. Because the zip code might span 2 districts. Or
Well, basically what you do, it doesn't make sense in this sense, but basically what you do is this. Right. So you lead it back into the past.
Okay.
Right? Good. This was multi-dimensional ER modeling. Very simple, very easy to use, very, very clear, also to non-experts in the field. And this is the beauty of the design, because it can be automatically used for the conversion into a logical schema. But on the other hand, it's very understandable, so you can talk to the application people about what they need and what they want, right? And it's very easy to show them, okay, how do you aggregate? Do you aggregate by week, or do you aggregate by month? Or do you use the year, or do you have a concept of a fiscal year or something like that? Do we cater for that, right? And they can immediately talk with you about this graphical model, right? They will immediately understand what you do. And this is kind of nice. And this has been embedded into the unified modeling language too. The idea of UML is that you can extend it for all the different applications and for all the different requirements that you have for certain scenarios. And so you tailor your model to a certain domain by using stereotypes, which basically means you add new elements, so-called tagged values, give you new properties, and then you can put constraints on top of it, which kind of defines the semantics that you do, right? And it looks very very similar. So if you have multidimensional UML, you just have to add a stereotype, which basically is the fact node like we had in MER, and then you need the granularities and so on. And basically then you can work with the icon, with decoration, with the label of it, or simply with the fact alone, right? But you can create these artifacts in UML. That has been done for the fact stereotype, for the measures in the sense of tagged values. So basically you can either have the direct value, which is the measure, or you can perform a computation on the value. So for example, if you need taxes or something like that, and you know the tax is 18%, value added tax or something that comes on top of the net price, then you can also have a formula where you go and add the taxes, or this is kind of units sold times unit price. So this is the total amount of money that you created, right? The revenue that you created. Good. And when you do it, it looks kind of very similar to what you do. You have the fact class in the middle, right? With the sales, and the sales consist of sold products, and then you have these dimensions, right, that are kind of the same thing, again alternating or just in a single way, right? And then you can just roll up on this kind of way. So it looks very similar to the multidimensional ER, and it is basically the same. It's just a matter of notation, right? So the concept that you need to extend the ER model or the UML model for multidimensional data storage is a fact node that has measures, a granularity that is combined by a binary classification edge for each dimension, right? This is everything you need. Then you have a multidimensional model already there. Fantastic, isn't it? Yes. Okay. Summary for today. So we talked about different architectures. We talked about the basically the vertical and the horizontal architecture, right? The idea between those are you either distribute, you either separate the ETL process from the actual application, right, in the vertical process. Or for each of the different applications, you build its own ETL process, right? So you can reflect different requirements of the data marts or of the way of dealing with data directly encoded into the ETL process. So you create a little bit of overhead there, but if you need strongly differing requirements for your applications, that might be a good idea to partition it horizontally, right? So this is the basic idea. We talked about thin client, thick client architectures, right? Where is the actual computation done? We talked about the distribution of warehouses, especially in a global world. So this is or globally economic world. This is very, very necessary today. Can be centralized, can be geographically distributed, can be technologically distributed. These are the cloud or the web scenarios. We talked about data modeling. So the data model that we need for data warehousing is multidimensional as opposed to the one-dimensional data models that we used to work with. And I showed you how to extend the classical ER modeling or the classical UML modeling such that you can also use multidimensional models there. And the basic idea is you have the fact nodes, you have the measures of the fact nodes, you have the dimensions that are associated with the fact node, and within the dimensions you have different granularities that are connected by binary classification edges. Good? Questions? No. Then in the next lecture we will go on with the data modeling, and since we did the conceptual modeling today, I will show you how to do the logical model, and I will show you how to do the physical model, right? So down to the storage. Thanks for the attention, and that's all, folks.